Okay, brilliant. So I'm Alison O'Mara-Eves from the UCL Institute of Education. And today I'm going to be talking about how we're trying to manage the information deluge, which in the morning session there was mention of the term data deluge. So it's the same kind of concept that we've got more information than we can currently deal with. And one thing I just want to point out in the title is it's quite appropriately a title of two halves, because I'm starting with how this information deluge needs to be managed, and it's actually driven us to seek out TDM processes to kind of assist with this. But then the second part is thinking about, well, now that we're starting to integrate these TDM processes and technologies into our workflow, how is that actually changing what we're doing with research? So we're kind of working our way through the life cycle of how TDM is interacting with the research that we do. Lots of people to acknowledge. I particularly want to acknowledge my colleagues James Thomas and Claire Stansfield who work in my team. Some of the slides in here have been developed by those, but lots of other people and lots of different funding sources. This isn't just one project we're working on. There's a whole list of different funders that we have for lots of different projects. So this is a bit of a culmination of where we're at with our thinking in terms of TDM with systematic reviewing. So to start with the data deluge, there's an increasing amount of research and there's much more information than the typical policymaker or practitioner can use. They don't have enough time to digest it all. And people have been talking about this for a long time. Back in 1972, Archie Cochrane, and if anyone here is familiar with the Cochrane collaboration, this is the Cochrane. He basically wrote a report that said there's so much data out there, so much information, we need to start bringing it together, quality assessing it, so that we can make meaningful recommendations to doctors and people working in hospitals about what sorts of interventions they can be doing to help common illnesses and so on. So someone's already talking about how we start to synthesize information. And it was only a few short years later in a different discipline of educational research that Jean Glass introduced the concept of meta-analysis. And I kind of laugh at this little snippet from the paper now, because he says in there, in 5 years' time, researchers can produce literally hundreds of studies on IQ and creativity or... Well, okay, so literally hundreds may have been appropriate then, but it's obviously much more than that now. So in response to this recognition that we have more information than the people that need it can digest it, we started to develop systematic review and meta-analysis procedures. So the whole point of a systematic review is to avoid bias, do a rigorous synthesis of all the evidence on a given topic in a transparent way that's hopefully, ideally, replicable. And there's a few key steps to a systematic review for anyone who's not quite familiar with the concept. But we basically start by searching for, in theory, all of the available evidence on a particular topic, or as one of my information scientist colleagues really enforces, our best sample, because it's almost impossible to get everything. We don't know what we haven't found, basically. So we try and find as much as we can on a given topic, and then we screen the studies for inclusion in the review. So we basically set up some criteria at the start of a review that allows us to make decisions about which pieces of evidence actually help us address our research question. We then extract information from those studies about the population or the intervention itself, outcomes, the research methods used. We kind of pull out as much of the information from every single study that we've found as being relevant, so that then at the next stage we can analyse or synthesise that data. And from that analysis, we hope to be able to draw conclusions across the body of evidence. And systematic reviews and meta-analyses are used across a range of different disciplines and different topic areas. But just as an example, we recently completed an update of a review where we were looking at smoking cessation interventions for pregnant women. So we searched far and wide across a whole range of different psychosocial interventions, found ones that were specifically related to pregnant women, and tried to draw some conclusions about what types of interventions actually work to help support women quit smoking, and looked at a range of different outcomes, such as whether the interventions actually reduced the number of smokers, reduced the number of cigarettes if they were continuing to smoke, whether they maintained abstinence, and then also outcomes for the infants. So were there differences in the birth weights of the infants for the quitters versus non-quitters? Were there differences in the rates of stillbirths and so on? So we look at a whole different range of outcomes from this evidence, all about this one topic of how do we help women quit smoking when they're pregnant, to be able to make recommendations to policymakers or practitioners about what sorts of interventions might be useful and helpful for these populations. So that's a very brief introduction to the concept of systematic review, which was introduced to address this need of policymakers and practitioners for synthesised and summarised information that's reliable and robust. But over time, things have changed. So Jean Glass mentioned several hundred studies in 5 years. Well, if you see, this is a tweet from Web of Science 2 years ago, June 2015, where they celebrated having over 1 billion cited references in their database. This is insane. That's a lot of research that's being conducted. If we look specifically just at biomedical research, so narrowing the field to biomedical, PubMed is now saying they have over 27 million citations on biomedical research alone. So crazy numbers that we're talking about. Too much for systematic reviewers to deal with now. It's just, the problems keep expanding, I guess. So the data deluge grew, and now systematic reviews are basically taking too long and costing too much money. We put in funding proposals to organisations like NHR to do systematic reviews on really critical topics like smoking cessation interventions for pregnant women. And it's difficult because the length of time that it takes to do this rigorous process of identifying all the research and extracting it thoroughly, they're not cheap, these projects, because they take years. And we're also not getting the results out there as fast as people need it. Now, in parallel, the computer science technologies have been developing, and things like text mining, natural language processing, machine learning and artificial intelligence has been developing. And so some clever people said, we have a data problem where we have more information than we can deal with. Maybe computer science has a way of helping us. So our team and others, there are pockets of teams across the world, mostly in the UK and in the United States, some in Australia as well. But there's teams working on exploring whether these sorts of technologies can help with different parts of the systematic review process, including searching, screening, extracting information and analysis. So the next part of my presentation is a bit of a whistle-stop tour where I'm just going to show you very briefly a few different ways that text mining and machine learning has been applied to these 4 different parts of this systematic review process, with some examples of tools. And I just want to have a disclaimer at the start. I haven't chosen to present these tools necessarily because they're the best available or the only ones available. It's more because they were easy to present in a screenshot in presentation of this length. If we were in a 90-minute workshop or something, I would probably do live demos and present a range of different tools for each of these. But these, just to give you a sense of how people are actually using text mining for these different processes. So first I'm going to start with a little bit of research that one of my colleagues at the Epicenter, Claire Stansfield, she did this work on how can we use text mining and machine learning for assisting in the search aspect of systematic reviews. So a typical systematic review starts with someone coming up with a list of search terms and usually doing a Boolean search where they identify through lots of different databases. They might, if it's in health, they might search PubMed and Medline and CINAHL and a whole range of different databases to try and find as many references that look vaguely relevant as they can to start with. But what we're starting to see is that there might be ways that text mining can help with the development of the search strategy, so the actual search terms that we put into into these different databases. And so what you can do is you can start with a sample of citations. So a few that you already know are relevant to your particular review question. And look at the citation elements of those example citations. If you don't know any to start with, that's fine. You can do a random sample based on some keyword searching and use those as your starting corpus. But the key is getting some citation elements to start feeding into the text mining process. And then there's kind of two different ways at the moment, two different ways you can go from there. So on the left-hand route, we have what's called text analysis. And it involves looking at word frequency counts, phrases, or nearby terms in text. And this is kind of actually probably the most common one at the moment. You may already be using this and not even realize, because it's actually already integrated into some tools. But a lot of them have been developed for specific databases like PubMed. So they work very well with PubMed. And basically what they do is come up with a word or phrase list, or sometimes a visualization like a word cloud, to show you what kinds of key terms are appearing in that corpus of documents, the sample of citations that you put in at the start. And what that does is gives you a bit of a glimpse as to what is the nature of these titles and abstracts that you've identified at an early stage. What kind of key terms are interesting? Perhaps there's key terms that you hadn't thought of yourself, and so you can add them to your search strategy. So increasing potentially recall, but also increasing precision, decreasing precision perhaps. But it can also help flag up when there's irrelevant terms coming up. So you might find that there's a subset of studies. One of the reviews I worked on was looking at interventions to help people learn to cook food from scratch. And there was this whole subset of literature that came up through the searches that was around food poisoning related to fish that had been undercooked. So it was you could see from the search strategy why these records had been detected, but they were completely irrelevant to what we were looking at in our review. So these sorts of tools can help you to identify either terms you hadn't considered, or terms like bodies of evidence, subsets of evidence that you just want to screen out quite automatically because they're irrelevant. And so you might be able to introduce not if you're then developing a Boolean strategy from that, for example. So that's kind of the text analysis. You've also on the right hand got term extraction and automatic clustering. Now these are slightly different because they use statistical analysis like TF-IDF, or statistical and linguistic analysis, and a good example of this is work from our colleagues at the National Centre for Text Mining, where they've developed a free-to-use piece of software called Termine. And basically what's happening here, it's a little bit more complicated than just word frequencies and counts. It's actually looking at the relationships between terms within documents and across documents. So it's, I guess in a sense, a little bit smarter. But you can use the same sort of process, is put in some documents that you know to be relevant or a random sample and help figure out are there clusters of studies that you're picking up that are more or less useful, and basically adjust your search strategy based on what you're seeing in those the outputs of these analyses. And again, same thing, you'll end up with word or phrase lists or visualizations like word clouds, or there's also, I don't know how to describe them actually, the topic models that kind of show where clusters of studies hang together based on the terms that are included in those documents. And all of this is assessed by humans. So we get the outputs from the text mining and machine learning. Humans look at it and see what's useful, and you take the useful information from those results and use it to revise the search elements. So it comes back, and then you can repeat the process if you want, or perhaps you're quite happy with your search strategy by then. What we're talking about here is not necessarily making the search process a whole lot faster. It may do, because you may find some ways to determine what's very relevant that's being picked up by your existing search strategy. The key thing is it's helping to make our search strategy more efficient. So hopefully what we are getting is more likely to be relevant. So it's kind of this concept of precision. That's some examples of how you can use it in searching. And, I mentioned that Claire had done a lot of this work on it. So there's a paper that only came out a couple of days ago in Research Synthesis Methods, where we talk about some case studies of where we've used this in actual systematic reviews, and different tools that we used and whether it was helpful or not, the kind of pros and cons, because sometimes it doesn't always work. So it's useful if you're interested in going down this path, because we try and give a bit of a balanced perspective on it. So I'm going to move on from searching now onto screening, because this is where actually most of the research and development investment has been. Basically, there's a massive database on this now, or not database, evidence base on the use of text mining and machine learning for screening. And what they generally involve is training a machine on a few samples of what a relevant study looks like, so one that meets your inclusion criteria, and then on what an irrelevant or excludable study looks like. So you're kind of trying to teach the machine what would be an in case, what's suitable for your review question, and what's an out case, so what we don't want to see. You train it on some examples, and then it then goes off and tries to predict whether any new instances are likely to be relevant or not relevant to your particular review. And these kind of semi-automated approaches are actually the most common. So we've been discussing throughout the day that people are reluctant to remove the human element out of text and data mining, and that's very much the case here. People feel more comfortable when there's still a human involved in assessing whether the machine is getting it right or wrong. So there's very few people at the moment who would be advocating that we just let the machine go off and make the decisions. Most people are advocating sort of more semi-automated approaches. And we conducted a systematic review of text mining processes or technologies for systematic reviewing, the screening aspect in particular. And we found that there across the different studies, and we had 44 studies, evaluations in that review, and depending on the discipline that it was applied in and the actual type of classifier or algorithm they were using, the workload reductions were in excess of 30% and up to 97%. Now, a workload reduction of 30% may not sound that exciting, but we often have reviews that are well in excess of 10,000 titles and abstracts that we have to screen manually. Most of them are more around the 40,000 mark. So you're talking several months of a human sitting there going, yes, that's relevant, no, that's relevant, just reading titles and abstracts. So it's painfully boring, it's error prone because of fatigue and things like that, but it's also incredibly costly. So 30% of 40,000 titles and abstracts is actually weeks and weeks worth of work saved. So it's more exciting than it possibly sounds. 97% is fantastic. That's like, we don't need to have this job anymore. Do ourselves out of a job. But the summary of the conclusions from that systematic review that we conducted is that there's three main different ways that people are testing out how they can use text mining in systematic review screening, just the screening phase. One is this notion of screening prioritization. And what that does is basically you give some examples of relevant and irrelevant studies, and the machine then ranks all of the remaining documents that you've identified through your search strategy from most likely to be relevant to least likely, and the human starts screening them. So we're not actually getting the machine to automatically classify as include or exclude, it's just ranking them. And we've labelled that as safe to use. There's basically no real risk or major risk of it because a human, at least one human, is still manually screening every single title and abstract. The risks that are small, and we're evaluating through a process evaluation, and Charles actually just touched on that in the previous session, is this idea of, I guess, motivation is part of it, or user fatigue. You get all the relevant stuff at the start, and then you have this long tail end of junk that's not really relevant, and so potentially a bit demotivating and could be error prone there. But that's screening prioritization. The second way that people are using it is using the machine as a second screener. It's quite common in systematic reviews to have 2 or more independent people screening every title and abstract to make sure that they don't make a mistake, because people do make mistakes. And so what these approaches are saying is you still have one human screening everything, then also the machine's screening everything, and then check the discrepancies through a human checking the discrepancies. And we've said that that is generally safe to use with care based on the evidence that were included in our review, because the human is still screening everything. The problem is questions around what threshold do you use for a discrepancy, because a lot of the classifiers have fuzzy boundaries between what's an include and an exclude. They might give a label of this is an exclude, but it's very near the boundary of what could have been an include sometimes. So it's trying to define where those boundaries are that mean that a human really should triple check that decision. And the third use is automatic study exclusion. So this concept here is basically we train the machine with a few known includes and excludes, may do some monitoring of it at the start, but then we reach a point where we say, actually, we trust that the machine has found all the relevant stuff and we can exclude all the rest of the junk. In some areas, it's actually, the performance is looking pretty good. In very clinical areas where you have a very well-defined clinical condition and a drug treatment, the terminology is quite specific, so it actually works quite well. But we're seeing not such good result, less good results in social sciences. So that's why we've kind of marked that as a, still, it's promising, but still in development, needs a bit of work in some domains. So, someone asked in the last session whether there's any evidence that these machines work. So this is from a series of reviews, 6 different reviews from the Cochrane Heart Group. So these are all related to different heart conditions, and they're systematic reviews. And basically what we have on the x-axis for each of them is the number of items screened, from 1 to most of them around the 5,000 to 10,000 mark of titles and abstracts that were screened. And on the y-axis, we have the number of includes that were correctly identified, so the number of studies that should be in the review that were identified. Now, if we were screening at random, in theory what we should have is these kind of the dotted lines that have just appeared, where the includes are randomly dispersed throughout our set of studies that we're screening, so that as you continue screening, going from the X to the Y, 0 to 1 on the 0 to the N, whatever the number of records are on the X-axis, you would just gradually find the includes throughout the corpus. They'd be dotted throughout randomly. What we see with using the text mining is that the includes all get found very early on, and then it kind of plateaus, and that means it's not finding any more includes as it continues going through the list of records. And you can see for the different reviews, performance does vary. So we have some, like this one, and this one, and yeah, that one, where it's a fairly straight line. It picks up a lot of the includes very early on, and then that's it, it's done. There's not much more to gain. This one up here, the performance is less good. It's still much better than random identification, but it takes a while for the machine to actually find all of the records. And likewise with this one. So we do see differing performance even within clinical topic areas like heart conditions, but in general it's it's actually detecting most of the relevant stuff pretty early on. I'm just conscious of time, so I'll just quickly move on to cost effectiveness. So someone actually did a cost effectiveness evaluation, and I'm just going to highlight that there is some loss with using text mining to replace humans. So in this example that they did, they found that there was, for those who like the terminology around recall, the using single screening supplemented with text mining, they only had recall of 95%, whereas if you have basically 100% screening, human screening, then they had 100% recall. So what, in this particular data set, it was equivalent to 8 studies were identified using humans only that were not identified using text mining, okay? So the text mining process missed out on 8 records. And what that means in terms of cost effectiveness, it cost 35,500 extra pounds to have humans screen everything, which is equivalent to 4,500 pounds for each of those 8 records that were identified. So they're pretty expensive. Those 8 additional includes cost a lot of money to find, is what we're saying here. Whether it's worth it or not depends on whether they make a difference to the results of the review. So if we missed out on finding those 8 studies, would our conclusions change? That is the big challenge for us because we can't know that in advance. We basically have to find those 8 studies to see whether they would have made a difference, which means we would have to invest that human time. So there's evidence that there's a bit of a trade-off. We may save time and money, but we can't really assess what we're losing in terms of the actual knowledge and information that's being missed. So I'm just going to skip through here now to, there's a pre-built classifier has been developed using data from the Cochrane collaboration. Basically, the Cochrane collaboration has a massive database of every review they've ever published, but also every single trial included in every single review they've published, which is equivalent to a very large number. But then they additionally have this concept of the Cochrane crowd, which is very similar to the volunteer basis that Charles was just talking about with the Wikidata, in that we get humans to volunteer to label titles and abstracts as whether it's a randomized controlled trial or not. So it's a pretty straightforward task. There's a little bit of training given, but people just assign a label. RCT, not. So 280,000 records were used as the training data for this classifier. And now what it can do is you can put in any corpus of studies and apply this classifier to it, and it will tell you whether it's likely to be an RCT or not. And because it has this massive database of a training data set of 280,000 records, it actually works pretty well. So you can see from this plot here, it assigns a score of how likely it is that a study is an RCT or not. And in this column here are all the ones that it thinks it's very unlikely that it's an RCT. And this up this end is, yes, it's probably an RCT. And if we actually trusted the machine and got rid of this column here, so the stuff that the machine thinks is very unlikely to be relevant if you're doing a review of RCTs, then you would only miss about 0.1% of the studies. So there is some loss of relevant studies potentially. So some things the machine said were RCTs, were not RCTs, but they actually were, so false negatives. But this is the important thing, is that we eliminate 60% of the workload. And when we're talking, as I said, tens of thousands of records, this is quite a massive effort saving for a small loss. So a lot of what we're looking at now is this trade-off between what information we might lose compared to how much we gain. Very quickly, extracting information is quite another issue. This is an example of a piece of software called Robot Reviewer. And in this particular one, The key thing is it actually makes a decision about, or a classification as to whether a study meets a particular population characteristic, an intervention characteristic, or contains particular outcomes, and it presents the snippets of text on which it bases the judgments. So in this one, it talks about blood pressure and so on, and it said this is how it made a decision about what type of population it's included in that primary study. So this here is a primary study record. You can also use text mining for analysis. So in systematic reviews, we like to do critical appraisal or quality assessment or risk of bias assessment, whatever terminology you want to use. But it's basically checking that the evaluation, the primary research, was actually done in a sensible, legitimate, sound methodological way. And the machine can now make a good guess as to whether certain risk of bias criteria have been met. So this example here, one primary study, they've said, yes, it meets the condition of, they used random sequence allocation, so it has a low risk of bias on that dimension, which is why it gets a little green plus sign. And this is the text that it used to support that judgment. So you can see it uses things like participants are randomized via a computer number generator, blah, 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 blah. So it provides the text from the primary study to support why it made that judgment call. And when it's got this little red box with a question mark, that's just saying it either wasn't reported in the study or there was conflicting information. And again, it presents any supporting text directly from the study. So you can still, as a human, make a judgment about whether the machine seems to be right or not. So I'm not going to have time to go through this, but I just want to highlight that Cochrane Collaboration is quite a good early adopter of these technologies because they're investing lots into trying to help text mining and data mining and machine learning for systematic reviewing, and they've introduced it throughout this whole evidence pipeline. So I suggest if you're interested in this, it's worth probably Googling the Cochrane evidence pipeline to see just how they're using text mining in different ways to save us lots of time. But I'm just going to skip through all this because we're out of time. But this one might be of particular interest though. This is just one part of the Cochrane evidence pipeline where what they've done is they've trained classifiers using their back history of hundreds and hundreds of reviews, thousands and thousands of trials included in those reviews, to train it to identify when a new study comes in, whether it's likely to be relevant to a particular review group. So review groups are based on topic areas like dementia, airwaves, movement, there's a whole range, but basically any medical or clinical condition, there's a Cochrane group that tries to cater for. And so any new studies that come in, it tries to triage it to the relevant group. So we're saving people time of having to do constant searches to see if they need to update their review. There are other early adopters, so we're actually doing some work with NICE to set up a surveillance system very similar to what I just mentioned. So basically it will trawl the internet for any new publications and then send it through to the particular guideline development group if it appears to be relevant to their guidelines. And this will be really helpful in helping to identify when we need to do review updates and guidance updates, because if there's new evidence coming through that might perhaps change our conclusion, so it'll give an estimate of how likely it is that a given new study will change the evidence conclusions and mean that we need to update the guidance, it'll tell us to do that. So this kind of surveillance system is helping us keep on top of research in real time. A related project to that is actually from the behavioural science discipline. So they want to do a similar kind of surveillance system, but in behavioural science. So if you're interested, I recommend looking at the Human Behaviour Change project. So in summary, how is text mining, machine learning changing what we're doing? We might start moving from search strategies to using PICO definitions that are based on classifiers that have been trained on extensive back catalogues of data. we might start talking more about data extraction, less about data extraction, more about structured data. And structured data is the terminology we use for what people this morning have been talking about in terms of metadata that's in a machine-readable form. So think machine-readable here. These kind of surveillance systems for updating reviews and guidelines, evidence synthesis in real time, and changing the nature of systematic review. So it's more about trying to validate what has actually been done with the supplementary help of text mining, rather than spending lots of time just searching and screening for studies. Key considerations are, it's one of these kind of glass half empty, half full situations. We've got the benefit of reviews are more timely and less resource intensive, which obviously appeals to the end users of our products and the funders of our products. But there are likely to be some risks, and we need to consider, and that's where we're at now, is thinking about how willing are we to take these risks. So things like the possible introduction of bias. If you train a classifier on a particular set of data, is it then going to predispose the machine to identify more studies like that? Also this idea of loss of comprehensiveness. So I've already noted we're not reaching 100% recall. So are we worried about missing those odd studies? And a reduction in transparency is probably a big one, because people don't like black boxes a lot of the time. Sometimes it's nice to know someone else is getting on with it and they know what they're doing, that's fine. But stuff like this, people feel a bit uneasy about, because, well, particularly systematic reviewers, we're quite pedantic about making sure we've got all the information and we're not missing anything. So this idea that we might miss stuff and not know what we've missed is a scary thought for a lot of systematic reviewers. There's a very short selected bibliography. I've got more extensive ones. I've also got lists of tools that you can use, so you can email me if you want them. And just to flag this website here, the SR Toolbox. So if you're interested in tools for doing systematic reviewing, there is a subsection on there for text and data mining tools for systematic reviews, because someone else has asked about that this morning, more broadly, but not specific to systematic reviews, but that's a good website to check. So email me, I'm happy to share the slides or any other information that you might need or want. Sorry, that went way over.